Okay, in this next slightly more complicated torsion example, we've got the same shaft we had in the first example, 18 foot long, has a 4-inch diameter, but now we have multiple torques being applied here. So we have non-uniform torque. Now, the nice thing about this, of course, is that within each segment, the internal torque is going to be constant, so we'll be able to use our basic models. We'll have to keep track of whether or not we're still in the elastic range or not. But we've got three things that we're asked to find here: the torque diagram for the member, magnitude and location of the maximum shear stress, and the angle of twist at the free end, that's here at point A, relative back here to point D. And keep in mind, as always, our positive sign convention. Right hand rule, stick the thumb in the outward normal, and the curl of your fingers on that right hand is going to tell you what the positive direction turns out to be. Right? When I look at this, I'm going to guess that we're going to end up with a negative rotation because we have sort of a net of 15-foot kip trying to torque this thing in one direction and only 10-foot kip going in the other direction. Let's see what ends up happening. Okay? So that torque diagram just comes from the free body diagram at each section. Right? So out here in the far right, at the end at A, we have a 4-foot kip torque, right? Fingers going in the direction of the arrow, and positive outward normal. This would be the internal torque in segment AB. And if we sum torques along this longitudinal axis, of course this has to be opposite to oppose that. So we're going to end up with, out in that segment from A to B, a minus 4 kip foot torque in that segment. Right? Now when we come and chop this, here's A, here's B, and C is out here to the left. We chopped in between B and C. We then have this 4-foot kip there. We've got the 10-foot kip going in the other direction at B, and again we'll have this outward normal, that would be TBC. We sum torques along the longitudinal axis, and we've got 10 going in one direction, 4 in the other. BC is going to have to be 6 to make all that sum to 0. So we're going to bounce up then down here on the diagram to a positive 6, and that will be constant. Notice how this is just like the shear diagram would look like. And then finally we get this one all the way that we're cutting between C and D. We have one more applied torque at 11, and we get that 4 going to the left. We got the 10 at B going to the right. We have at B 11 going to the left. We've got that positive outward normal. That's the reaction at D, also equal to the internal torque at, between C and D. And now we got 15 going to the left, 10 going to the right. This is going to have to be a minus 5 for that to be all in equilibrium. So we'll bounce down. And in kip feet, there's your torque diagram. Right? And that's going to help us greatly when we want to answer the next question, which is find the magnitude and location of the maximum shear stress in the structure. Now, remember our model, our basic model, is that our shear stress, our max, is probably going to be equal to then TC over J, but we want the maximum combination of all that. Now C is the same in all segments, J is the same in all segments, but T is what's going to vary here. So since C and J are going to vary, all we have to do is go find the place where the internal torque is the maximum. J for this solid cylinder is pi over 2 times our outer radius to the 4th power, so that's pi over 2 times 2 inches to the 4th. That's going to be 8 pi inches to the 4th. Okay, so we can go with this as our model, go back to our torque diagram, J is constant everywhere. We just need to find the max torque. That would be in segment BC. And so tau max then equals 6 kip foot. Convert it to kip inches times our outer radius, 2 inches, and then over our J, 8 pi inches to the 4th. And let's see what we get. 6 times 12 is 72 times 2 divided by 8 divided by pi, and that's going to be equal to 5.73 KSI. Right? And we're not going to worry too much about plus or minus. This is plus because the torque was positive. Okay, so that's going to give us then our second part, and then the third part was to figure out what the angle of twist is of NA relative to D. So there, what we're going to do is we're going to apply the basic model, which says that phi equals TL over JG for any segment in which the torque, the J, and the G are constant. But we don't have that here, so instead what we'll have to do is we'll have to sum up the effects by keeping track of sign. This is where the torque diagram is going to be particularly useful. Right, so J and G is constant for all these, so let's factor that out right off the bat. We got 1 over J, that's 8 pi inches to the 4th. G is 11,000 kips per square inches. Right, and then we only have to deal with a combination of T and L in each segment. We've got a 5 kip foot, a negative, a positive 6 kip foot, and a negative 4 foot kip. All foot kips. So let's do that conversion out front, 12 inches per foot. And there's also going to be the length, which will also get converted, so we'll have another one of those 12 inches per foot. So that in the inside, walking left to right, minus 5 kip foot of torque times a length of 8 feet, then plus 6 kip foot times a length of 6 feet, and then minus a 4 kip foot times a length of 4 feet. Someone was being clever in the design of this problem. And so that part's going to be minus 40 plus 36 minus 16. So we're going to get a net of negative 20 kip foot squared times 144, which gives us kip inch squared in the numerator. And then divide by 8, divide by 11,000, and divide by pi. And we have a net angular change or rotation from left to right of minus 0.010 radians. And again, the negative sign already tells us the direction. This is the one case you really do want to use the absolute sign convention. It means, though, if you look back at this section, put your thumb down, positive outward normal, that would be the positive direction. It means that this thing actually rotated the other way. If you were sighting down the end of the barrel, you'd see a clockwise net rotation, right? This would be clockwise in here, this would bounce it back the other way, and this would bounce it back again. And that just follows that torque diagram, going one direction, another direction, and then back again.